Good afternoon, or evening, in fact. Hello. So, I think we're running 7 minutes early, but I think since this is the last talk of the day before the happy hour, I may just begin. So, welcome everyone to the last talk of the day by me, Laura Nolan. This is called What SRE Could Be. And there's a bit of an elephant in the room here, which is this. I work for this man who is the conference chair. When I put this talk in as a sort of a, I guess, rebuttal or response to his talk, which was the SREcon America's keynote last year, I did not work for him. So the situation has changed on the ground. Anyway, so Niall writes books and occasionally rips them up. And I'm also the author of one of the chapters in this book, the SRE book. So I think I agree with Niall on quite a lot of things, but I also want to say that I don't think things are as hopeless as Niall thinks. I think that there's a bunch of stuff we could do to make things better, but things are not as hopeless as Niall thinks. I should also say, as part of the conditions for me joining Niall's company, Stanza, he agreed that I can say whatever I want in public, and accordingly, he has not vetted this talk. So he doesn't know what I'm about to say at all. So let's claim that, let's hope that Niall's claims that he's a social democrat are accurate so that I don't get fired. Anyway, in lieu of one of those boring biographies, I've worked for FANG companies and big tech and stuff, and I've worked for smaller companies. But, given that we always say that SREs are T-shaped engineers, we have a bunch of broad skills and maybe one or two areas of depth, I thought I would just introduce myself with my T-shaped skill chart. So I'm terrible at a whole bunch of things. I'm terrible at Go, and I'm terrible at Prometheus, and I'm terrible at Terraform and J2EE from my old post-college jobs. And I'm also a terrible historian and philosopher. I have degrees in those things. It turns out that everybody who works for Stanza in Ireland has a degree that is not directly tech relevant, which is fun. But my main skill set is trolling. And I am here to troll an entire industry because we have work to do, people. We have work to do. We have an identity crisis in our field. And you can see it even from the talks today. What even is this thing? How many times today have we seen talks that attempt to define SRE or that, that sort of argued that SRE is poorly defined in some way? I think at least 4, including some of the plenaries. This is a crisis, right? Are we operations? Are we engineering? Can operations be engineering? I think yes. Do we write code? is YAML code? Do we have to be on call? There's a whole host of unanswered questions. But it's okay because these are the wrong questions, and I'm going to convince you of this. And of course, it's Andrew Clay-Schaefer this morning in his really good opening plenary, or second of the opening plenaries, said that we're moving up the adoption curve. We've gone from the early adopters who were very focused on sort of SRE and very deep in it to a lot of new faces, and that's great. But it does lead to all these sorts of questions about what is the right way to SRE. And it also leads to a lot of stuff like this. What is this? Pillars of SRE. I have a lot to say about the pillars of SRE. These are lists of stuff that we might do under some circumstances. These are superficial practices. Again, to hark back to what Andrew said. They're ritual without reason. This is just a sort of salad. So we had a bit of an internal conversation about this, and I was, doing my trolling bit. And, I think that obviously SREs have good taste. We have good taste in architecture. We would go for classical pillars like the Doric, Ionic, Corinthian, Tuscan, and Composite. But then my equally trolly colleague Blake, who is probably somewhere around here, said, well, caryatids, obviously. And I think he's right, Then he said something very dubious about the practitioners of DevOps and their use of the old school sort of Egyptian pillars. I just want to make clear, we love DevOps. DevOps and SRE, they have a very clearly defined philosophy, which I'm going to talk about in a second. We don't. We have the black hole. The only true pillar of SRE is some poor schmuck on the end of a pager wrestling with these terrible tools that we have. Yeah, these are the pillars of SRE. We should feel bad. So, I think that when we say that things like observability and incident response and so on are the pillars of SRE, it's kind of like a bunch of architects saying, well, glass and wood and concrete, these are the pillars of architecture. No, it's not. What we're doing is we're mistaking the obvious attributes, like the things that we can see, for the essence of what we're trying to accomplish. And these are not the same things. Architecture is about more than the materials. It's about making structures that serve a purpose, like workplaces or homes or public spaces, or even just showing off, like in this case. And we have that covered because we have Kubernetes and service meshes and all this kind of stuff. So, okay, just to, as an apology to DevOps, because we, kind of slagged their pillars, DevOps actually has a pretty good coherent philosophy. And probably somebody here will tell me that I'm wrong, but from a bunch of the books I've read about it, there's a fairly focused sort of philosophy that looks at lean manufacturing, kind of the good old Toyota days. And you have this very sort of clear objective of we deliver small changes frequently, we create fast feedback loops, we make it safe to deploy all the time, we eliminate bottlenecks, we eliminate friction, and this creates the ability to make change safely and quickly, and it's foundational to high-performing IT organizations. Now, this is a coherent philosophy because it's a set of things that sort of make sense together, and it can give you direction and guide you about what you're doing, right? They're not saying the pillars of DevOps are Jenkins and GitHub Actions. Those are tools that they use. They are not the philosophy, and we should not mistake the two. What is our SRE philosophy? Black hole. Or is it? So, this was Niall in his talk last year. SRE is a donut hole in a donut hole, and the hole is not at the periphery, but at the center. Clearly paraphrasing Knives Out. We can do better than this. So, I think one of the problems that we have is we have certain practices that are what I would call systematizable. And that means that you can pretty much apply them to any system in more or less the same way. If you want to introduce SLOs, it's going to be relatively similar between different systems. Okay, you're going to have to choose different service level indicators and be a bit thoughtful about the type of the system. Not everything is a web app serving requests. There's pipelines and all sorts of things. But we can build a product that you can configure to compute your SLOs and show you pretty graphs and do things based on that. And the same is true for incident management. If you can pretty much take those FEMA incident management principles and kind of slap them down in any organization, do a bit of training, introduce a Slack bot, everything is good. It's standardizable, okay? And some kinds of automation are also standardizable. GitHub Actions, I think, is actually a great example of making that sort of tooling much easier in many ways. Now, these are not bad things. SLOs are fine. Incident management is fine. Automation is fine. But we can't substitute that from a coherent guiding philosophy of what we're doing, right? It makes us very shallow when we try to do that. This isn't an engineering discipline, right? We have a bunch of less standardizable things that SREs do. System design and improvement, architecture type work, review work. This can be anything. I can't plonk what I did for organization X down in organization Y and expect it to make sense. The same is true for anomaly investigation and incident review. These things are always context specific. Every incident is different. Every anomaly is different. If I want to do risk analysis activities, every system is different. It always depends on context. It's very hard to build standardizable products that will help you do this. The same is true for building, say, control planes for your systems, which is a thing that has increasingly become part of SRE work in the past several years. You know, every context is a little bit different. Every system has its own quirks. Again, monitoring and alerting, you need to think about the context of that system, what the constraints are, what controls you need to impose. And disaster testing, to do that well, you should think about that particular system and its weaknesses and you know, what it's doing, what context it's in. This is the work that's not cookie cutter. And this is also the work where the best SREs that I have seen and that I've worked with have excelled. This is work that can be really high impact, but I cannot go and consult for your company for 3 hours probably and change the needle on any of this stuff. I can't build a product that's going to meaningfully do this work for you. This is sort of the essence of the difficult part of what we do. And because there isn't an easy way to standardize this, we talk about it less. And this is, I think, partly pointing towards that donut hole, that black hole at the center of the profession. You know, a lot of the good stuff is hard to articulate and hard to standardize. So here's my definition of what I think SRE is. I think it's understanding systems and making appropriate interventions to make them function better. So it's hard to sort of, this is something that's a little bit sort of fluffy, a little bit hard to put our fingers on, but we're going to try to in this talk. I can tell you what it's not. It's what Liz Truss's government just did in the UK, right? That was a bad systems intervention. But we can make good systems interventions. But to make good systems interventions, we have to think about that as part of our work. If we approach our work and we say, okay, what we do is observability and SLOs and automation, we're not going to get to some of the hearts of some of the systems problems that we might solve. So the tasks basically are, we have to build mental models and ideally actual models that we can share of our systems and how they work. We need to go a little bit deeper than the typical sort of, 3-block architecture diagram. We need to figure out what the pain points and the problems and the risks are in our systems. And then we have to try and intervene to fix those problems without making things worse elsewhere, like the UK governments, and proactively apply expertise to avoid foreseeable problems in changes that we're proposing to make. So there's two things here. There's both the technical systems that we work with, the code and the infrastructure and all this stuff. And then there's also the human beings that work on that system. And I cannot improve on Effie's amazing talk that she just did. But we need to think about that too. I mean, the systems are not just the technical components, they are the people and how we work with the systems that we build and operate. The core thing about systems is systems are the sum of their components interacting together. It's not just one thing that you can zoom in on and fix. It's the whole thing. SREs do this already. At least many SREs do. And we do it largely by a kind of a combination of instinct and experience. We might call this wisdom. But there are some systematic approaches that we can use as well. Again, harking back to Andrew Clay Schaefer, we can steal some good stuff if we want to. Let's steal some good stuff. So what do systems interventions look like? What are some examples of what I'm trying to say here? So here's one example. Over the years, a lot of people who have run distributed storage systems of various kinds, a common problem is I want to replicate my data so I don't lose it if I lose an instance. But sometimes you're going to lose one of those hosts that's part of your system. So what do? You're going to re-replicate your data. Here's the twist. That's actually really bandwidth intensive. And it turns out that it's fairly common for hosts to drop off your system for a few seconds or a couple of minutes. A host reboots, or power goes out in a rack, or a network link goes bad and has to be repaired, or something like that. And it's also relatively common to have coordinated blips where you lose a few hosts at a time. So the system's understanding here is to say, okay, in this system, yes, we need our data to be re-replicated. But if we wait for several seconds, the system is going to be more efficient and more stable, and the increased risk of data loss is minimal. So that's a systems intervention. You're thinking about not just the one host that you have lost, those few pieces of data that are in need of replication. You're thinking about the whole system and how it works together. Another good systems intervention that we've seen in recent years is this idea of cellular architecture. So a lot of companies have been using this and it's going back at least 10 years, probably 15. But it's a really powerful system level pattern. So the way you do this is you're running a platform and you have a lot of users, and what you do is you assign each user to a particular cell of your application, which is its own vertically integrated set of business logic, data storage, and so forth. It's its own little unit, its own little chunk of your service. The power of this as a systems intervention is if I have split my application into cells and assigned users to cells, I now have a way of doing realistic rollouts. I can roll out to dog food or test cells, and then I can gradually roll out to the cells in my application while monitoring. And this gives me a realistic way to test things in production without risking the whole thing. And it also it gives you limited blast radius if one particular customer starts to effectively DDoS your service, which that's the thing that customers do. We all know that. So it's a powerful systems level pattern. It's something that you do at the level of a system, not at the level of a single binary or piece of code, right? Here's another one I like. Who here reads Hacker News? I'm sure some of you do. Only 2 people? 4 people, okay. Right. It was fun. It was a fun popcorn experience there. About May this year, they lost both of their redundant RAID arrays at once, or more or less at once. And that was because the firmware in those devices had a counter that was ticking up every, I forget if it was microsecond or millisecond or second, but it was counting up over time, and it hit a threshold, clocked back over to 0, and broke irreparably. And this happened on both of their servers at once. And this kind of thing is sort of in those repeating patterns. Incrementing counters don't always roll over gracefully. But there's a really nice little systems intervention here. Some organizations always initialize their incrementing counters to be close, instead of 0, to be near the maximum. And that's a systems intervention because it means that when they do testing, they always see that rollover. So that's a really cool little sort of holistic way of viewing, not just this counter, but that system that the counter is embedded in and the testing processes around that. So systems interventions are cool, right? This is a real thing. This is work that people do. It goes deeper than just slinging YAML or tuning alerts. And we need to sling YAML and tune alerts, don't get me wrong, but we need to do this kind of work as well, because this is the core of SRE as an engineering profession. But we have social systems as well, and we have SRE kind of social systems interventions, because our computers are us, or our systems are us as well. They're not just the computers and networks and programs. So think about on-call rotation size. A lot of organizations with SREs, they set a minimum on-call rotation size because we know that very small on-call rotations lead to burnout, and then they risk collapse if a bunch of people burn out at the same time and leave. Then you have a team that's inexperienced, experiencing churn, and it becomes very difficult to make improvements on the system. So you require a minimum on-call size. You include developers if you don't have enough SREs. You should maybe have developers anyway. I mean, Dave O'Connor's talk this morning was great. SLOs and error budgets are actually more of a social systems intervention than anything else, because what they're supposed to be is that signal about how we should prioritize work, how the human side of the system should respond to signals about reliability from the technical side of the system. Then blameless, or the modern version, of course, is blame-aware, postmortems and incident reviews. This is a social intervention which is really important, because if you have, I don't remember, people remember the bad old days of, you would break something and you would get blamed for it. Hopefully nobody lives in that reality, but if you blame people for causing problems or triggering problems, then people will conceal information, your organization cannot learn, risks get swept under the carpet, and your system is not going to move towards a better state. It's bad all around. So blameless incident reviews are a social systems intervention. Automating toil is as well. So toil is work that scales with the size or usage of your system, and that could be automated. So things like turning up clusters or provisioning data stores in a system is toil type work. Turn ups, turn downs, that kind of thing. Anything that's routine and takes a bunch of time. We like to automate that, because if we don't, what happens is our team becomes overwhelmed with this kind of work, and we have no time to do any other engineering, and we end up in a hole. So social systems interventions are important as well, and all of these are thinking about the health of the system, not just, we don't have SLOs just to hit the SLOs. We have the SLOs to provide the signal. We don't have blameless or blame-aware incident reviews just to have them. We have them for reasons. So thinking about that systems context of what we do. So systems thinking is an actual discipline, or in fact, I guess a collection of a number of disciplines that focuses on understanding and optimizing systems. This book is really great, and some of the techniques I'm going to talk about next come from that. In fact, most of them do. This book is very much aimed at practitioners rather than, say, researchers or academics. It's not specifically aimed at software engineers, but the authors have tried really hard to make it concrete and practical. So we're going to look at some of the techniques from this book. Engineering a Safer World by Nancy Leveson is another one that's worth looking at. Some people have quibbles with her STAMP method, and it is quite heavyweight, but it has some good ideas as well. Was anyone here at SREcon22 in Dublin? Yeah, so you'll remember Nancy Leveson's talk. Donella Meadows is known more for non-engineering systems. She's thinking about sort of social level problems, but her book, Thinking in Systems, is a great kind of introduction to systems ideas. She's also known for a book called Limits to Growth, which basically argues that we're running out of stuff. Let's hope she's not right, because she thinks we're running out of stuff about now. Yeah. So this is kind of the systems thinking hairball, a whole bunch of techniques. I don't expect you to even be able to read most of this. But there's biology, maths, computing, all this kind of stuff kind of comes under this umbrella. So the biology stuff would be looking at things like cooperative behaviors of anthills and bird flocks and fish schools and so forth. Then cybernetics and control systems and artificial intelligence. Well, we don't need to worry about this. A system. What is a system? We all kind of intuitively think we know what a system is, but it's relatively hard to define, so we'll define it for you. It's got to have three things. You've got to have elements. You've got to have interactions, connections between your elements. And here's the actual kind of interesting part. Your system has to have a function, something it is doing or trying to achieve. So a tree is a system, and a school of fish is a system. They're all doing things. Your body is a system. A computer is a system. A cube cluster is a system. It's systems everywhere. And to some extent, drawing system boundaries is a bit arbitrary, and that's where the function comes in, right? If I want to say, okay, the system I am looking at has the function of running Kubernetes pods, then the Kubernetes cluster is the right system to think about. If I'm looking at the system that is serving my user requests, then the Kubernetes cluster is part of that system. So the function that you're trying to analyze, it dictates where you draw those boundaries. Now, complex systems are a special subcategory of systems. And I think probably most of you have seen Richard Cook, his great paper, How Complex Systems Fail. Complex systems are special. They contain multiple components, not just one. They have non-linear interactions, which means I can make a small change here, like change a configuration, and it can have a large effect somewhere else. This is the butterfly flapping its wings. You have to have feedback loops, and then you can get these amplification effects, these vicious cycles that we see. You have to have interactions with the environment. If your system is just a box that doesn't interact with the environment, then it can't have a useful purpose. So interactions are needed. Complex systems are always dynamic. They're not just sitting there. There's always something happening in them. There are processes that are going on to maintaining them. There are things flowing through them. They're moving. They're dynamic. And they have state and history, which affects how they will behave in the future, which is one of the things that makes working with complex systems so challenging, right? You go to do something today, and it may not behave the same as it did last week, because it's dynamic and it has a different state today. So these are some of the challenges that we're dealing with, especially as we change our systems over time. So these are dangerous things. And just a warning for all the parents here, a seasonal warning, they have found some complex systems in Halloween candy, so watch out for that. Okay, nobody's into that meme. So we live in this post-cloud and post-DevOps and post-SRE world, and I made a typo in this slide. Anyway, so what it's supposed to say is we are not astronauts anymore. In the sysadmin days, you had your pet systems, and you would go and you would configure them by hand, or you would run a script and you would watch that script run. You'd be pretty hands-on. You'd go and you would manually change a load balancer configuration instead of having your health checking system come and do that for you automatically, right? We were hands-on. And now we're not. We're mission control, right? And we've built these robot astronauts and sent them into space. We are the mission control, and we are building these systems that run our systems now. And that is a subtly different business to be in. And it is subtly different because now, to make changes safely, we need to understand not only the system that we are working with, the system that's doing the work, serving the requests, churning the data. We also have to understand all of the pieces of automation and control planes and things, the infrastructure that we have built around and under that system. And that is a significantly more complex task. So we needed to do this work to scale, but now we have this really sort of hard problem, right? And at the same time, we're no longer hands-on with the systems that we're trying to operate. We're hands-off. We don't often get to see the direct impact of what's being done by the things that we're working on. So our systems have become a little bit sort of mysterious, right? So can we use systems approaches to solve these complex systems problems that we have? And I think we can. And this comes from some of the authors of that handbook in systems thinking methods. They wanted to do an experiment to see if these, in fact, were just fluffy academic kind of approaches or if they're useful to practitioners. So they did an experiment on the Death Star. And here's what they did. They took a bunch of students in their engineering courses and they gave them the specs of the Death Star, which you can buy. This is Star Wars, by the way. I'm sure everyone in the room has seen it. Apologies if you have not seen Star Wars, because I am going to ruin the movie for you now. So they wanted to see if the students will be able to use sort of traditional deterministic analyses based on the components of the Death Star to find critical risks and problems in the Death Star. And they also wanted to see if students could use systems thinking techniques to find problems and risks as well. And indeed they did. They gave them the same 4 days that the Rebel Alliance had to figure out how to destroy the Death Star. And the students did great work. They did in fact find the problem with the thermal exhaust port. And they recommend fitting a grill to solve that. They found 21 other problems. Here are my favorite ones. So they could have used soft power to entice the stormtroopers to create an insurgency. They could collide the Death Star with a planet or sun by hacking the Navi computer. They could invert the artificial gravity and so on. So I think this is a pretty powerful technique. You know, if they can come up with so many creative ways of attacking the Death Star, maybe we can come up with creative ways of improving our systems. Because I don't know about you, but every system I've worked on has had a bunch of problems. And we often find them the hard way. So ways of using the systems thinking tools. Describing and understanding the systems. Modeling them, if you will. Evaluating risk and analyzing incidents. Those are the three sort of big use cases that we have for systems thinking techniques. We are doing a lot of this informally. We have informal systems thinking in SRE. So we do pre-mortems, which is when we are looking at a new system or maybe a system we're running already and we're saying, okay, how can I break this? What are the risks that we're concerned with? Tabletop scenarios for a similar thing. Disaster testing, doing it in practice. Wheel of misfortune, often used for training. You know, walk people how they would investigate anomalies in a system and understand them. And incident reviews, where we're looking at something that really happened. But the problem with the way we do this is because it's so informal and so much based on the individual sort of experience and expertise and the shit we've seen, it's very hard to give that knowledge, that understanding that we've developed of our systems to someone else. Maybe a new person on the team, maybe our other teammates who have a different understanding. And it's very difficult to train junior people to do this work. We always complain that senior SREs are hard to find. It's because we're training each other using stories and fairy tales and parables. You know, we haven't systematized it yet. So the first kind of tool for describing systems is one called cognitive work analysis. And in the, 15 minutes I have. I can't obviously go into depth at all of these methods, but the Handbook of Systems Thinking Methods covers all of these. So cognitive work analysis, it basically consists of 4 levels of analysis. You look at the purpose of the system, you assess performance, or methods of assessing the performance, which is effectively SLIs. You look at the functions in the system, and the processes and objects. And you do this and you sort of break that system down into chunks that we can see. So instead of like bits of automation hiding in the corner or sort of this little, control plane cron job thing that's running every 5 minutes and everyone's forgotten about, you try and you bring these processes out in the open. Control tasks are a first-class citizen here. So we look at what tasks could be done in what situations. When is it safe to do something, and when is it not safe? And that's a form of analysis that we rarely actually do. This tends to be a thing that's very implicit in what we know, or maybe it's in a run book somewhere. We don't ever do a structured analysis of this work. Strategies, how do I move the system between states? These are states we would intend to be in, and also states that we don't intend to be in. So things like, if this system is overloaded, how can I shed traffic? If this system is malfunctioning, how can I revert to the previous known good release? That sort of thing. And it also includes a level for the people. So the social analysis, what is the team that's running this? What contact do they have with other teams? How do they work with the system? How do they understand what the system is doing? And what competencies do those people need? So that's, a lot of this is, again, like I say, stuff that we kind of do in an unsystematic way. So we could be more systematic about it. Then hierarchical task analysis is another kind of similar approach. So basically, we, again, start with goals and sub-goals. This is a very common sort of way of describing systems. And it's really interesting. Instead of thinking about, we go to describe a system and we say, okay, well, there is a web app and there is a database here and there is a cache over here and there's Kubernetes, right? We draw these boxes, but we don't talk about the functions and we don't talk about the constraints and the reasons why work happens. So in hierarchical task analysis, that's what we're focused on. So we're looking at the goals, sub-goals, operations, and plans. A plan is a sequence of steps that you do. So plans can be linear, or they can be branching. They can have if statements. They can be continuous. So every minute do a particular thing. They can happen at particular times, maybe triggered by particular conditions. So you end up with like a big tree that includes all of your automation work, all of your control planes, and also all of your human work. So very simple example, we might have an overall goal. I want to serve user requests. The sub-goal is I'm going to ensure sufficient healthy capacity, so I'm going to auto-scale based on CPU. I'm going to use blue-green rollouts. You could probably go into more depth on that one. I'm going to alert a human if I'm serving 5xx's, and so on. And you would probably have a bunch of other plans. And this is a way that we can represent all the stuff in our systems that we always forget when the person who set up that cron job leaves the company. The other thing about this is, if we actually take the effort to describe this work and show it to our colleagues, they will probably say, and you forgot that. It gives us a way to start aligning our mental models with each other. And that's really powerful as well. It can also surface gaps. Someone says, oh crap, we're doing all this, but we should be doing that as well, and we have no actual controls or processes for that. So these approaches, they socialize knowledge of these sorts of control paths in our systems that are very often a little bit implicit, because we don't build systems that show rollouts and configuration update mechanisms and credential rotation and auto-scaling and traffic shifting and backups and resharding and all of the control stuff we do. We just it's off in the ether. We don't draw it, right? But they're really important. And that's where I think things like HTA can help. So here's a story. Years ago, I worked on a system. It was a giant distributed database. And we had this outage report one day, and clients were saying that they were not able to get fresh data when they queried. What was happening? Everyone was like, So we had to go work it out from first principles. And it turned out it was this. The data was versioned, and clients had a way of looking up what the latest version of that data was, and by default, they would query that, unless they were told for consistency reasons to query at an earlier version. So one day, the little piece of control logic that published that version broke. And also the monitoring that was supposed to monitor that kept increasing broke. And it turned out that was all so old and had just worked for so long, everyone had forgotten about it. It wasn't on any diagram. Maybe it was in some runbooks somewhere, but we didn't find them. So we don't have to forget that these kinds of mechanisms exist. If we had these in our diagrams, we would probably do better, right? So then we come to sort of modeling behavior and modeling risks in our systems. And there's a technique called EAST-BL. The BL stands for broken links, and I forget what the EAST stands for, so homework, look it up. And what it does is it starts with the hierarchical task analysis. You extract a network of tasks, so how do the different tasks in the system interrelate? And you look at how information gets shared between those tasks. And that could be between just computer-based systems, like the version number between the clients and the database servers. But it can also be between people and computer systems. So then what you basically do is for every single link in that system, you say, what if that broke, what would happen? And not just what if it broke, what if it was wrong? What if there was way too much of it or way too little of it? And this is a great basis for doing your design reviews of any system, or tabletop scenarios, or wheel of misfortunes, or disaster testing. This is such a useful thing. And it doesn't actually necessarily take a whole lot of work. If you've done some analysis of what those sort of links in your system are, those control actions, it's relatively easy to do this. Then another great tool is this one. These are causal loop diagrams, and some of you may have seen them. Marianne Bellotti at last year's virtual SREcon did a talk where she talked about this. It's from a thing called system dynamics, which is quite a venerable systems thinking method. But basically what you do here is you look at loops and you look at quantities in your system. So this is a little diagram here that comes from an article I wrote a few years back. about cascading failures. And the thing here is you notice that you've got a loop. And that loop looks like this. You've got service load per instance. As load increases, your latency from that service increases. As latency increases, you eventually see timeouts increase once you pass a certain threshold. As timeouts increase, clients will start retrying, and then your load increases. And so we can very clearly write this out, and we can show that this is a vicious cycle. In causal loop diagrams, we have two types of loops. We have the reinforcing loops like this, the vicious cycle loops, and we have balanced loops. So for example, a way to make this a more balanced loop is we put in an inner loop that puts in some sort of throttling, for example, on retries or circuit breaking. So this is a systems thinking practice that lets us see these sorts of cascading failure risks and mitigate them. It's also really useful for just documenting how people think about how their system works. And it's entirely possible that if I asked two people working on the same system to talk about how their system behaves under particular scenarios, they might draw different causal loop diagrams. And that's interesting because one of them knows something that the other one doesn't. It's a way of uncovering what people know. If you can, and you'll need to work with them to, get them to actually sort of, do something in this format. Most likely, there's a little bit of art to this. But if I learned it, then you can learn it, almost certainly. Lauren said this morning in the very first opening talk that we learn by watching good people work. And he is right, but we can also do more to learn by watching how people think. And this is a way to watch how people think. This is quite powerful, I think. So we're talking a lot about models, and models is something that keeps coming up. And we're like, we don't have good enough models. Models don't have to be perfect. I'm here to tell you that it's okay to have models that are kind of crappy if they're useful. Here is a secret. All models are inaccurate. All models are inaccurate because all models simplify. If a model doesn't simplify, then it's exactly as complex as the situation on the ground. Now, some models, they simplify a lot more than others, but all models simplify. And when we look at engineering, as a sort of a broader discipline, there's a lot of physical engineering practices that are more rules of thumb than something that's backed up by hard science. And they get used because they work. And we can use these kinds of models because they work, even if they're not perfect. If we're building our systems to incorporate these principles of control and sort of feedback and moderation of these sort of runaway loops, then we don't need perfection to create stability. We build a system that adapts by itself. Okay, getting towards the end. So we don't think about hazards in our work explicitly, and these are other concepts that are to the fore in certain systems thinking practices, particularly Nancy Levison's STAMP approach. So what her way of doing this is saying, okay, what are the hazards in our systems? What constraints do we need to keep our systems in so that we don't run into these hazards? And what controls can we use to make sure that we don't exceed these constraints? So an example here, caches. Has anyone ever had a problem in their systems because all your caches restarted or got invalidated and they were cold and now your databases can't handle the load? I see a lot of hands. Yeah, me too. It's terrible. Okay, so this can happen. So a lot of people say, okay, well, we will have a cache only for performance, only to reduce latency, and we will keep enough serving capacity so that we can serve from our databases, or whatever source of truth you have. The problem is this is really hard. How do you make sure? So the systems thinking sort of way of looking at this says the hazard is that we can't serve from database and we lose our cache. The constraint is we need to make sure that our databases can serve all of that load. Then we can start thinking about solutions to that. One of the best ones I've seen actually just says, well, asynchronously, after every cache hit, go and query the database anyway. Then you have this really tight sort of control that says your database, yes, it's expensive. There's always trade-offs. But that's a way of making sure that you don't actually ever outrun that capacity of that database without knowing about it. I'm just going to skip over this because of time. So we talk a lot about being data-driven. It's kind of like the Silicon Valley religion. We are data-driven. Okay, data is not bad, and it can really help us to construct these models that we're talking about. But there are other ways of actually understanding than sheer dint of having data about everything. And that is good, because if we're trying to evaluate risks in a system that we haven't built yet, and we're just looking at the design, we don't have data by definition, unless we've built a pretty extensive prototype. Then the other thing is, we don't have data on the risks we're avoiding. So there's many, many sort of big holes in what we can do with data. Systems thinking gives us ways to reason about outcomes based on the structure of the systems that we're building. And we should use that to enhance our reasoning. People who always say, well, we're not going to make any decision unless we have data that shows that it's right, they're missing a lot of tricks. And I think systems thinking can fill in a lot of those gaps that we have when we try to reason about the world using only data. Yes, I'm being very controversial here. So what I would say, kind of wrapping up here, is we need to be flexible. I've thrown a bunch of quite heavyweight methodologies out here and said, these can help us, and these can help us. But do we need to do them all of the time? No, we don't. I mean, obviously we can't all go and spend 50% of our time drawing HTA diagrams. But maybe we could spend 2 or 5% of our time doing that. And maybe it would make us more effective at what we do the other 95 to 98% of the time. I think it would be good to start doing this, just the places where our systems are scary and risky and painful. And I think we could get a lot from it. And I think it's one of these things that can level us up as an industry. So going back to where we started with the SRE book and ripping it up, and this suggestion that we're going to have to apologize for it. Yes, the SRE book is terrible if we think about it as a how-to manual, because you are not Google. And even at Google, it wasn't a how-to manual, because that book was written by people from a whole bunch of different teams doing a whole bunch of different stuff. But we think about it as a zoo of systems. This is something from Donella Meadows' book, The Systems Zoo, a bunch of examples about what we can do. A bunch of things that worked in context. Maybe some of them can work in your context. Or maybe they can inspire you to find systems interventions that do work in your context. So think about it as inspiration, not as a how-to manual. So this is my call to action. Systems thinking is our special sauce already. We just don't talk about it. We can surface what the most experienced and most effective and most brilliant SREs are doing, and we can systematize it so more people can do it. And we can start thinking about these concepts like goals and plans and links and hazards and constraints and controls as the first-class citizens in our engineering discipline that they should be. And that's it. That's me. Thank you.